Welcome to Simple Linear Regression Video 2. I'm Elizabeth A. Albright of the Nicholas School of the Environment. This video will cover residual standard error, also known as standard error of the regression. We will go over standard error of the slope coefficient and test the significance of the slope coefficient. Thank you for joining along. So if you remember back to Simple Linear Regression Video 1, we worked with data on daily family income and consumption for a population. The daily family income values range from 80 to 260, and then the family consumption expenditures, those are the Y, and remember our Y values are a random variable where we are assuming our X's are fixed. Our Y's are probability distributions given our X values. And we can calculate the conditional means of the Y's, or expected value of Y given our X's. What we did in the previous video is pulled two different samples, and here I have plotted them with two different lines. Sample 1 is in green, sample 2 is in blue, the population is in that pinkish orangish color. And so this is important as we think about tests of significance. Right, so each time we pull a sample, there's sampling error. Our sample's going to differ. The standard deviation is going to differ. And so when we think about inferring from a sample of X and Y and that coefficient of the relationship between X and Y, we need to think about this variability when we infer back to the population. Because remember, we typically do not know the population. I'm just putting the population there assuming that we know it. It is knowable, it is fixed, but it's typically unknown, the population. So what are we doing? We take a sample regression function and infer to the population regression function. So our sample regression function is y hat, or predicted y, equals beta naught hat. The hat means predicted. The naught means that's the intercept, plus beta 1 hat times x1, and that's from I equals 1 to n, the number of observations. And then we have the u hat, or the predicted error, and that's yi minus y hat I. And that also goes from I, 1 to n. And we use the sample regression function to say something or to estimate the population regression function. And remember from video 1, our population regression function is the expected value of y given x equals beta naught plus beta 1 x. So if you remember back to the video, we pulled a sample and calculated a simple linear regression equation. We arrived at this through using ordinary least squares, or that's the mechanism that R used to calculate the intercept and slope. And remember that ordinary least squares, it minimizes the squared distance of the difference between the observed and the predicted y values. So we used ordinary least squares. We got the equation y hat equals 0.509 times income plus 24.5. So we can interpret that as a dollar increase in daily income is associated with a 51 cent or $0.51 increase in predicted daily spending. So our beta hat 1 equals 0.509, and our beta hat naught is 24.5. Here is the mechanics. Here are the mechanics in R. I put in the data. Income.sample is our X. Spending.sample is our Y. I made a data frame and I ran the linear model. And R gives us the coefficients, the intercept, and the slope. Slope of 0.5091, intercept 24.4545. Estimate of the slope. And typically we are most concerned with estimating the slope, especially when we get to multiple linear regression. So now we need to think about residual standard error. And this is a measure of the spread of the distribution of yi around the regression line, or around that predicted line. And there's a lot of confusing terminology around this concept or measure. Wooldridge, the text Wooldridge, calls it standard error of the regression. R calls it residual standard error. Some other texts call it root mean square error. But they all mean it's a measure of the spread of the distribution of yi around the regression line, or around the y predicted. And we can calculate that. So I'm going to step you through the calculations of residual standard error. But first, let's go over the equation. Residual standard error equals the square root. And in the numerator, it's the sum of yi, or the observed y's, minus the predicted y's at I. All of that difference is squared, all over n, number of observations, minus 1 plus k, where k is the number of variables in the model. So here, we don't need to do this typically. R will do this all for us, but I'm just showing you the mechanics here. In the column A, I have yi, or our observed values of y. Column B, I have the observed values of x. Y hat, as you can see in the equation up here, is the predicted values of y using our x and y values. So equals y hat equals the intercept plus this b2, or the x times the slope coefficient. So I calculated out y hat. I then calculated out the error, and again the error is yi, 70 minus y hat, 65. 65.2 gives us about 4.8. Carried that down, filled that down, that's our error. Took the squared of the errors, and again I'm just following this equation here. And then I summed the squared of the errors, and then I divided by 8 because we have 10 observations, minus 1 plus 1, and then took the square root, and I got 6.493 as the residual standard error. And again, this is a measure of how far away are the observed y values from the predicted line. So luckily we don't have to do that. R does it for us, and it is highlighted here in the orange. Residual standard error, 6.493 on 8 degrees of freedom. That 8 degrees of freedom is the n minus 1 minus k, or the number of variables in the model. So in this case we have one variable in the model. We also subtract another one for the intercept, and so we have degrees of freedom of 8 and a residual standard error of 6.493. Perfect, it matches up with our calculations in Excel. So standard error of the slope coefficient. This is a measure of precision of our estimator. This is very similar to the standard error of a sample mean, for example. And this allows us to conduct tests of significance. Right? It's a measure of how precise our estimator is. So let's work through the math of the standard error of slope coefficient. So here we have our formula. In the numerator we have yi minus y hat, or predicted y, squared, all of that summed and divided by n minus 2. In the denominator we have xi, or the observed x's, minus x bar, or the mean of x, those squared and summed. So this should look familiar, similar to, or builds off of, the spreadsheet from before. And so again, for our numerator, we are calculating the errors, the yi minus y hat. We are squaring them. I summed them here. Then we divided by 8. In this case, that's the sum of the squared errors over n minus 2. And we get 42.16, roughly. Great, that's our numerator. Now our denominator, I needed to make a new column, and this is xi minus x bar. Again, xi are the observed x's, and x bar is the mean, 170. So for this first value, for example, we have 80 minus 170, which is 90 squared 8100. We do the same for each of the rows, right? And we sum that, and that is our denominator. We then take our numerator, divide it by our denominator, and take the square root, and we get 0.03574, and that is our standard error of the slope coefficient. So standard error of beta hat 1 equals 42.159 divided by 33,000, and that gives us 0.03574. Again, we don't need to do this. R does this for you. I am showing you the math behind the calculations of R. So now let's look at the R output. And there we go. We have our estimates of the line, the intercept 24.4545. Again, we're getting these from ordinary least squares. We have the estimate of our slope, 0.50909. And then now we have our standard error of our slope coefficient. I won't go into the standard error of the intercept. We'll focus today on the standard error of the slope. And then this allows us to do a test of significance, which is what we will talk about in the next slide. So, inference. We've done estimation. We've estimated the line. We've drawn the line through the data to estimate the population slope. And we did this using ordinary least squares, minimizing the sum of the squared errors. But now we know that we just pulled one sample, and that each time we pull a sample, it's going to vary, right? And so we need to think about tests of hypothesis, similar to what we talked about in comparison of means, right? So we want to test the population parameter coefficient is 0. A population parameter coefficient is 0 means there's no relationship. That would be a horizontal line. And we do this by calculating the standard error for our coefficients, which we just did, and then running a t-test and calculating a p-value. This should all sound familiar. It builds off of the concepts we talked about in comparison of means. So hypothesis testing. Test if the coefficient is 0. It's most often a two-sided test. We set up our null as beta 1 equals 0, and our alternative is beta 1 not equal to 0. And again, we don't have hats on our betas because these are population parameters that we care about, not the estimates or predicted. And then we have our t-value, or t-statistic, which is t equals beta hat 1 minus 0. That 0 is from the hypotheses, all divided by the standard error of beta hat 1. Right, so again, this should sound familiar or structured very similarly to how we conduct a test of significance. And in this case, our degrees of freedom for our t-distribution is n minus 2. And here we have our output. Again, from before, we have our estimate. We calculated the standard error. We have a t-value from the formula from before. That is the estimate minus 0 over the standard error, and we get 14.243. We look on a t-distribution, calculate a two-sided p-value, right? So the area greater than 0.14243 plus the area less than negative 14.243, and we get a very, very tiny p-value. And so this strongly suggests that our population parameter, our slope coefficient, is not equal to 0. So bringing it all together, our estimate suggests that an increase in $1 of daily income is associated with an increase of 51 cents in predicted spending. Right? That is our estimate of the line that we got through ordinary least squares. Then our inference, or our test of significance, says that the population coefficient for the slope is statistically significantly different than 0. And we report our p-value, p less than 0.001. We could also include the t if we wanted. So again, just to overview what we covered in the video, we talked about the residual standard error, or that is a measure of how far away the yi's, or the observed y's, are from the predicted y's, or the line. We talked about the standard and went through the calculations of the standard error of the slope coefficient, and then worked through a test of significance of the slope coefficient, setting up hypotheses and running a t-test, typically a two-sided t-test. So thank you very much for joining in today, and I look forward to seeing you in the next video.